We're going to discuss what makes coverage testing. Previously, we talked about requirements-based test generation using equivalence class partitioning, using boundary value analysis, and then we also discussed the test generation for predicate. And the predicates can either come from your understanding of the requirements or by just looking at the source code if you have it. Okay, today, the technique which we are going to discuss is purely white box based on the structure of your implementation. So it's called coverage testing. So the first question which we need to answer is, why do we want to do this type of testing? How does it improve your confidence in program correctness? We all know that we cannot use testing to prove the correctness unless you use every possible input value. That is exhaustive testing. And we cannot do it because it's too expensive. Okay. Then what is the option we have? We said we're going to discuss coverage-based testing. Then the first question you need to ask yourself is, how does this improve your confidence in program correctness? Instead of using a computer program and explaining how the bug in a program can be detected, we're going to use a different example, which is easier to understand the principle of coverage and the benefit of doing coverage testing, which is, suppose I ask you to find whether there is a stone on the floor of this room. Okay, so we have a floor in this room. That is the question which we're going to ask. We use this as the example for discussion, and later on we'll see how the solution, how the discussion with respect to this example can be mapped to a scenario such as is there a bug in a computer program? Okay, if we know how to search for a stone, then we probably can learn something from this example and apply a similar technique to help us determine whether there is a bug in the program. Okay, to solve this question, any suggestion? If I ask you whether there is a stone on the floor, what are you going to do?
I'm going to make a grid.
You are going to make a grid. That means you are going to do partition.
Yeah.
You are going to divide the floor into small cells. Good. Okay, so let's do it. Then the first question you need to answer is how big each cell should be. Right? So too big, the entire floor can be just one cell.
Right.
Too small, you are going to have many cells, and that is more time consuming. So the first question, how big each cell should be. And suppose, for discussion purposes, let's make it simple. We assume each stone is in a rectangular shape. It's not necessarily the case, but for the discussion purpose, it's a rectangular. Okay, so then is there any relationship between the size of each cell and the size of the stone? so that if I randomly select one point from each cell, and I find that there is no stone in each cell, then I can guarantee you that there is no stone on the floor. So I have to carefully decide the size of the cell, right? So any suggestion? Let's make it simple. Assume it's rectangular. Yes.
I'd make my grid squares slightly smaller than my stone square.
Okay. That means what he said is that the size of each cell is slightly smaller than the stone size. Assume we have different sizes for the stone. So we choose the smallest size. The size of the smallest stone. Okay, so what he wants is that the size of each cell is just a little bit smaller than the size of the smallest stone. So far, so good? Why?
That way, if it would be the stone, if it was on a square, it would be also covering a section of the surrounding area. So if I pick one and there's not any part of the stone in the square, then I know that the adjacent squares don't have it either.
So in other words, let's rephrase this, okay? I guess what he wants to do is that make sure, because the size of the cell is just a little bit smaller than the size of the smallest stone. So when you move this stone on the floor, okay, so it will what? Cell is a little bit smaller than the size of the stone. So one cell will be completely occupied, right? And then if I select any point from that cell, it will tell me there is a stone on that particular cell because this particular cell is 100% occupied. So it doesn't matter which point I choose from that cell. It will help me catch that stone. Is that what you want to do?
And that also tells me that there's stone in the surrounding, because it's completely covering the one, but it's extended out into the other squares around it.
Now the question is that for the adjacent cell, it's only partially covered. It's not 100%. So you randomly select one point from this adjacent cell. Now it depends on which one you select. You choose from this part.
Actually, the furthest part from the center stone on that specific square, on that other square, the one you were on, I picked a point on the other side of the halfway mark.
Here,
Just a little bit to the right of that.
little bit to the right here.
Yeah.
Okay, what can you conclude? Okay, you pick this point, right? And it says, no, there is no stone. Isn't this contradictory to what you just said?
Well, what I'm meaning is if it's on that near the right side.
This side?
Yeah, that would tell me whether there is a stone in the next one or not.
How can you tell?
Because the stone, if it's over the outside.
Yeah.
Yeah. Can I-
Yes.
Okay. Sorry. Okay. All I'm saying is, if I pick the point here and I don't have a stone,
Yes.
then this is the only stone here, because the stone would be coming here.
You don't know. The may or may not.
No. This is here. this is the border here.
Right.
So I would pick this point here, somewhere in here.
I think what he's saying is the next cell will also not contain the stone if it so happens that, that's what you try to say.
Yeah. The next one wouldn't have it.
The next one. But so the question is that then they based on the position of the stone,
Right.
right? So what you just concluded may change if I move the stone a little bit to the left, to the right, top, or bottom. So there is no guarantee. Then it's not so good.
I think as you said, I think the center one, if you test for each cell, wherever you hit it, that's the one.
What we want to do is what? I'm going to select one point
Yeah, the center point.
from each cell. Just one point, any point from each cell. If I observe no stone, then can I conclude that there is no stone on the floor?
In this case, yes.
In this case, yes.
Because if the square itself, I mean, if you're saying that
The cell is a little bit smaller than the size of the smallest stone. Is this good enough?
I guess you could.
I'm not sure.
In this case, for this particular position, I got one cell which is completely covered, right? So it doesn't matter which point I choose. I will detect that stone. Now the question is, if I move my stone a little bit
Yeah, right.
towards this direction,
It won't fly.
then none of the cell is completely occupied,
Right.
right? So if I move the stone to this direction, I end up with a stone here. I may choose one point from this upper right cell, this, here, and here. So I checked each cell, and none of them tells me that there is a stone. So my conclusion is that there is no stone on the floor, which is incorrect. So that means you did not find the right relation between the size of the cell and the size of the smallest stone. So what is the right relation?
So that it's always going to cover it.
It will be what? 1/2 of the smallest stone. So the length,
So that it would always be covered.
the length of each cell will be half of the length of the smallest stone. And the width of the cell will be half of the width of the smallest stone. Then in this case, ideally, you are going to have 4 cells completely covered by the smallest stone. And then you move around, no matter which position you put it, at least one cell which is completely covered. Right? So then you pick one point from each cell because one cell is completely covered. So I randomly select one point from each cell, and I found no stone, then it's guaranteed there is no stone on the floor. Because if there is one, then a cell has to be completely covered. Then any point from that cell will tell me there is a stone on the floor. Is this clear? So what you just said, slightly smaller than the size of the smallest stone, is not enough.
Yeah, this we are assuming that the stone is also aligned with the floor, right?
Not necessary. So
This orientation is like tilted for the 45 degrees angle.
oh no, we're talking about stone on the floor. Okay, so make the discussion simple. Right. Yes. So it's just flat on the floor. Okay. So that's why you can move. You can move the stone around But then doesn't matter which one you move. You want to make sure at any position, at least one cell is completely covered. Then in this case, you only need to pick 1 point from every cell. If the answer is no, then you are guaranteed there is no stone. So what does this mean? If you satisfy this condition, you pick one from each cell, means what? 100% coverage. Then that guarantees you the detection. Okay, for this particular example. So it's a good example, right? Now, the next question is that whether this can be applied to program testing. So this ensures that each stone covers at least one rectangle. If you give half width, half length, then it's guaranteed. And let's suppose you have limited amount of resources. You have to complete your testing within 8 hours. And you want to make sure that at the end of the testing, the probability to find a stone is less than P. Okay, so let's see whether we can accomplish this. So let's say, suppose for discussion purpose, we have the rectangular. So this is the dimension for the entire floor, dimension of each cell, and how many rectangles you are going to have, how many cells you are going to have. And we also assume to inspect each point, you need this much time. And you also need to transition from one cell to another cell, just like you need to set up the testing environment for the next execution and so on. So suppose altogether you have capital T. You need this much time in order to examine every cell. Then you need to make sure that the time which you spend is less than what you are allowed. But what if you need more time? So that means you are not going to be able to examine each cell. What are you going to do? Obviously, there are different options. So I cannot examine every cell. So I'm going to examine only part of it and make sure the time which I spend is less than what I'm allowed. But if you do so, then do you satisfy another constraint? That means the probability of finding a stone has to be less than P. So let's check. Suppose you have scanned a certain number of stones, and at the end, suppose you say, I still have this many stones, and I still have this many cells to be examined. So I have this many stones remaining on the floor. I have this many cells to be examined. I assume uniform distribution, so I can find the probability to inspect, to detect a stone. Right? So altogether, you have this many cells, this many partitions. You have this many stones. So when you check next cell, what is the probability for you to find a stone? Right? So this can be computed. And then you stop when the probability is less than the constraint, P. Okay. Now the question is, can we apply this approach to program testing? Can we say that, okay, I have 100 lines of code, right? I cannot afford to cover every one of them. So I'm going to cover 50 lines of code, and then I compute the probability, to find a bug in the program. If I say 100 lines of code, I cover 50 of them, I still have 50 to go. That is my denominator, 50, right? Suppose I know, 3 of the statements are related to certain box. Okay, can I do this? Can I say, I got 3 incorrect statements, I still have 50 not covered. So the probability, to execute 1 additional statement to help me find a bug is 3 divided by 50.
No, because you might not be able to weigh each statement the same. There might be some statements that run, 95% of the code is running during the runtime. And then some statements.
You mean the frequency?
Yeah.
Okay, assume they are the same. Just like here. I got this many rectangles, this many cells still to be examined. Okay, assume they are the same, they're all same size. Suppose they are all executed at the same time. Actually, the frequency has not much to do with the equation which we are discussing here. But suppose they are the same. So why it cannot be applied? There are a few reasons. First, you don't know how many stones in the field. Okay, ideally, you think, okay, I have this many stones, I have this many cells to be examined, so I can compute the probability. But in practice, you're still in the testing process. You don't know how many bugs in your program. You don't know how many stones in advance. So you say, okay, I only test, I have 8 hours. Okay, so I probably don't need to use that much resources. Right? So I just inspect certain number of cells, and I assume if I know how many stones on the floor, and I know how many cells still yet to be examined, then I can compute the probability, right? But this is under the assumption, yes, you do know how many cells to be examined. You know the denominator, but you don't know the numerator. How many stones? You don't. So what is the probability to find a stone by inspecting one more cell? You don't know. You don't know. So far, so good? So what should we do? Then we are going to say that I'm going to examine as many cells as possible. So in this way, I improve my confidence. So you think, I'm going to have everyone covered. In this case, it is true. And then what if you cannot cover everyone? You just continue until you run out of time. But people are not comfortable with this solution. You have 100 cells in hand, and you realize that you can only run 50. They don't feel comfortable. They don't want to see 50. They want to see 100. Right? So what is another option? I'm going to reduce the number of partitions. So previously what we said is what? Half size, half of the length, half of the width. I have so many cells which I need to cover. But the good thing is what? Because if there is a stone on the floor, you're going to find it because at least one cell is completely occupied. So it doesn't matter which point I select from that cell, it's guaranteed. But I cannot run the inspection against each cell because it takes too much time. So the first option is that you still go ahead, use the same partition, but you cannot inspect every cell. You just do as many as you can. People say that, how about, I just examine enough number of cells so that the probability of finding a stone in the next cell is less than P, right? So in theory, you can do it if you know how many remaining stones on the floor. But in practice, you don't have this information. So you cannot compute the probability. Yeah, there are some other ways, to help you do this estimate. But we're talking about the actual computation. That you need to have what? The value for the number of remaining stones. You know number of remaining cells which have not been examined, but you don't know the exact number of remaining stones. You can estimate, yes, but now we're talking about what? Compute the probability, not estimate. You don't have this information, so you cannot compute the probability of finding a stone by examining the next cell. Then you cannot say, okay, let's just examine enough number of cells so that the probability is less than the constraint. Therefore, I can stop. So far, so good? It doesn't work in that way. Then what do? Examine as many as you want, right? So you are not going to have 100%. But people don't feel comfortable. They would like to see a high number. And that is the option 2. How are we going to increase the coverage? We are no longer using the half size. We are going to enlarge the size of each cell. So I don't have this many. I only have half of the cells to be examined. So I require less resources. This can be done within the time constraint. Then the question is, what can you imply?
You can only have a probability, not guarantee.
Exactly. Because you can no longer say that if there is a stone on the floor, then at least one cell will be completely occupied. This nice property goes away when you enlarge the size of the cell. So it's no longer guaranteed, as you said. You can only say, probability. You have good confidence, but it's no longer guaranteed. So when you have 100% coverage, it's not guaranteed. The floor is stone free. So far, so good. So when the size becomes larger, the time required to complete the inspection goes down. But the probability of detecting a stone inside a rectangle also goes down because the cell becomes too large, right? So you may check a point which shows no stone, but the rectangle still contains a stone. So it's no longer guaranteed 100%. The larger the size, the probability for you to randomly select one point and inspect it, and the results will give you the actual picture, goes down. So let's conclude. So we have a computer program, we have the floor, we have error, we have stone, and so on. So based on the discussion which we just had, the coverage, you have what? Different types of coverage. That means what? The coverage with respect to the cell which has half size, or the coverage with respect to a cell which has a larger size. And you all have 100%. but they imply, different situations. So you can have your confidence, but it's not necessarily, the probability. So then how coverage can play in the actual program testing. So this is a well-known concept. Remember we discussed this before. For Christmas season, you go shopping, right? You have a known list of presents which you have to buy. Every time when you put an item in your shopping cart, you check it. That is coverage. So you're using this in your daily life. And we also talk about, when we talk, for coverage, it can be coverage with respect to requirements. Remember the triangle example? We say we partition the input domain based on the requirements analysis, and then we cover each partition. Right? So that is a different type of coverage. But for today, the coverage which we are going to discuss is the white box-based coverage testing. We're talking about source code. In particular, we're talking about each line of code. We're talking about each decision, branch, condition. We are also going to have a new set of coverage criteria, which is data flow based, that we are going to discuss in a few minutes. So this is the type of coverage testing we are going to discuss today. Okay, it's not just a black box. It's not just coverage with respect to requirements. We're talking about coverage with respect to source code. Okay. And in addition to give you good confidence, it also helps you monitor and measure the progress of testing. Right? So you have 30% covered, move on to 50%, move on to 60%. Right? This implies what? When you talk about coverage testing, there are a few things you need to keep in mind. The first one is measurements. You need to know what has been covered, what is still missing, right? Measurements. The next one you need to know is what? Enhancement. I got 100 lines of code. 60 of them already covered. I still have 40 not touched. How to generate test cases in an effective way so that coverage can be improved quickly. Okay, so every time when you talk about coverage, measurements, enhancement. So the topics which we are going to cover for today's lecture, first we talk about coverage testing versus code inspection, dynamic versus static, and then the relationship between coverage testing and the functional testing. And then we'll move on to the details of different white box-based coverage criteria. So far, so good? What is white box testing? The major difference between white box and the black box is what? Yeah. Black box, you treat everything as an entity. You don't look inside. And white box, you actually examine, how the program is executed, which part of the structure is touched. So you need to have source code. But what if you don't have source code? Then that depends. If it's written in a language such as Java, they only have bytecode, depending on whether it is encrypted. If not, I can still do coverage with respect to Java bytecode. Okay. Now, a more interesting question for you is, can we do coverage testing with respect to object code? What if I don't have source code? Remember what we said? Every time when you have a question that you cannot answer, what are you going to do? You're going to look for the solution. How to look for the solution? Google it to see whether there are any studies, which provides techniques to help you do coverage testing with respect to object code. And that's the way, you learn. Every time you're at work, when you face some challenges, you don't have a solution, right? You need to get help. You don't have an expert next to you. So if you are connected to internet, some of you are, just Google it. Can you tell me what did you find?
There's a book on Amazon about it.
About what?
Testing object-oriented systems.
Oh, that's different.
Oh, it doesn't have, I put coverage in my thing.
Coverage testing object code.
Coverage testing, object code.
It's not object oriented. Any of you? Have you found anything?
Object code verification, there's a tool that'll reverse engineer binary and debug it, like trace through the binary.
So there are various techniques to attack this problem. But that is beyond the scope of our
Yeah,
discussion.
it's not that simple. I mean, they make
No.
optimization, so many things.
Right.
they look at.
Right. But we ask you this question because you may say, hey, we discussed about coverage testing in class. Yes. And we assume you have source code. What if you do not have source code? Can we still apply the technique to a third-party application, to someone else's code?
You can put a wrapper on top of it and then.
Then it's different granularity. But you put a wrapper around someone else's code. This actually brings another interesting question. When you write a C programs or Java programs, right? The system or your program, which includes more than just the code which you write.
Yeah.
Agree? Okay, so when we talk about coverage testing, just the coverage testing with respect to your own code, or what you need to consider, because your program will invoke,
Libraries.
Lives,
Yes. Whereas
should
the-
we include the coverage with respect to that?
Yes, because your code depends on that.
Yes and no, depending on whether you have all the resources. No. So, but anyway, white box testing, we take into account the structure of the software being tested. And what's the difference between coverage testing and code inspection?
Code inspection is static and you go and then look at the code.
Yes, code coverage is static. You print up the source code, right? You actually what? Read the source code,
Yeah.
right? Then, is there any similarity between code inspection and coverage testing? Can you think of any similarity?
Yeah, in case of code inspection, you don't give any inputs, you are just examining the code.
Yes,
But in case of a code coverage, then you are giving some inputs to try it out.
one is static, one is dynamic. But think about code inspection. It looks like, you read this line of code, that means what? You okay this line of code. That means what? this particular line is executed, is covered, it's inspected, examined already, right? Just like a code coverage testing. You don't read the code by yourself. You let the system tells you whether this particular line of code has been covered. If yes, you mark it. So from this point of view, they are both examining whether this code has been gone through, either manually or that the system tell you. If you can only choose one, which one are you going to choose? Are you going to use static code inspection, or you are going to use the dynamic coverage testing? Conceptually, you want to examine every line of code, right? So you got 100% from the inspection point of view. You also want to have every line of code executed at least once. You have 100% from the code coverage point of view.
Yeah, but
So at the end, both approaches, every line of code is kind of examined. Okay, so if you can only choose one, which method are you going to choose?
I probably choose code coverage
Why?
because it's automated in the sense that it is machine. But in case of code inspection, what we normally see is the first page, all programmers thoroughly tested. Second page onwards, they won't be that thorough.
Yeah, because people are tired.
It's tired, yeah,
Right.
it's manual.
But there's a few weakness in your response. First, when you say coverage testing is automated,
You have to, yeah, somebody has to make sure.
I mean, that's a program. I mean, once you have, once you have given the rules of the program to the system, and then if it is testing the code coverage, then it is consistently testing the same thing. Right?
so pretty soon we are going to explain this, and in fact, that is your first project. So when we say automation, most likely we are automate the execution, not the generation. There are 3 steps. Remember, test generation, program execution, output verification, right? Execution. That's why in the project, in the first project, we give you a script. We ask you to write a script to automate the execution. But think about the test generation, it's still done manually. Yeah, there are some automatic test generator which we are going to discuss later on. But in general, the automation is for the execution. So to the question which I just asked you, if you can only do one of them, code inspection and the coverage testing, I think most of the people will say they want to do code coverage testing. Okay, the reason, there are many reasons. One of them is what? Code inspection, many times the errors can only be detected during the runtime because certain spatial combinations of the values and so on. And that is going to be extremely difficult for you to catch it, but by just looking at the code. Okay, that's very, and code inspection can be very useful to catch some syntax error. So or you have some coding standard. Yeah, coding standard, and then you say this one does not, follow the coding style and so on.
Yeah.
Okay, but so they I'm not going to say that which method is absolutely better than the other, because in the literature you are going to find some project which claim that they do the code inspection and they accomplish good quality. Okay, so maybe you can do that, but it's very unlikely that people are going to replace coverage testing by code inspection. They probably will do both, but if they just do one, I think most people will do coverage testing. You know,
But code inspection may not be feasible in certain environments. You know, I'm thinking large systems generating millions of lines of code. I mean, for me to count from 1 to 1 million will take about a month.
not just one programmer, they have a bunch of guys. Right.
Well, that's.
I mean, I think what I see with the code inspection is also if you have the domain knowledge, if the code has a real replication of the design, detailed design or not, with the inspection you will catch it. Even if the programmer has missed something or if has not taken some consideration, then if the guys who are reviewing it have the domain knowledge, then they know the design. So if that is properly replicated into the program or not, into the code, that with the code inspection you will catch it.
Can you think of one type of bug which is unlikely to be detected by coverage testing, but can be more likely caught by the code inspection?
Logic errors.
Logic error, okay, so it's logic error, I will argue either approach. Okay, so yeah, probably certain logic error by if you have very good domain knowledge. Okay, in addition to that, can you think of a different type of errors?
Maybe use the wrong size integer or something.
But that can be
That
can also be detected.
But if there are any system limitations,
I think what she wants to say was error of omission.
A big
Omission,
omission. That's the answer which I'm looking for.
omission.
That means missing code.
He said it before in the previous.
Yeah, this part, coverage testing, is going to be challenged. But code inspection, you can tell, hey, you miss the whole chunk of code, if then else, right? You only have then, you missed else.
no, but I thought that in code coverage, it says that there is missing else, there is a missing this thing, it will also come out, it will come back and saying that you have this thing, you have assigned these variables, but you're not using them, things like that.
Yes, coverage testing. See, now, coverage testing can also help you understand, probably something is
Someone-
missing.
Right.
Probably something is missing because it does not give you the correct output, okay? And then you trace down, you say, okay, it covers this if statement and then give me the output. So probably something is missing, but it's not so direct. Missing code is always challenging because it's not in the program. The code, you're trying to catch something which is not even here. That requires actual effort. If you just, incorrect assignment or if statement incorrect,
Or a comment in your else statement, if you had inadvertently commented a line of code out, you wouldn't catch that.
more challenge.
Yeah.
More challenge. So, but still, even so, due to the limited resources, so probably field and the field project are going to do the code inspection. Okay. How about the coverage testing versus functional testing? We all know what functional testing is, right? We have done the equivalence class partitioning, boundary value analysis, and so on. What is the relationship between these two? So in general, we emphasize that you always begin with functional testing. That is something which you must do. You have to do it. After that, you can think of additional techniques to help you generate test cases. So the whole idea is this one. You have so many possible inputs, right? That's your entire input domain. How to select only a small subset, right? So that if P runs successfully with respect to each test case in this small suite, it will not fail when you use a different input which you have not tried before. Right? So functional testing is always number one. And then you can use additional technique to what? Add a few more. So you can use this white box testing technique. Make sure every statement is covered. Okay, so actually that is the relation between the first and the second project which you are going to work on. Right, the first one is do a functional testing and submit a suite of test cases. And for the second project, you are going to measure the coverage of the test cases which you submitted for the first project. Right? That's what measurements. And the second part of the second project is what? Generate additional test cases. Take a few more to improve the coverage. As we mentioned earlier, coverage testing is not something new. That's been there for 50 or 60 years. You even have some tools, primitive tools such as TCAF, which can help you measure the coverage. And conceptually, I guess everyone agrees. You need to at least inspect the code before you can say you have good confidence. You have 1,000 lines of code, 700 of them never executed. How can you say you have good confidence? So conceptually, everybody agrees. You need to touch every part of the program. And the concept has been there 50, 60 years. Why it was not used before? 20 years ago, if you talk to people about coverage testing, they understood it. But no project reported, probably very few projects, 20, 30 years ago. They said, I got 80% of the statement coverage. But nowadays, it becomes much more popular. Now you talk to your colleague about coverage testing, they agree. They know what you are talking about. 30 years ago, they know, but they didn't do it. Why? If you know something is good, something can help you, why you didn't do it?
Resources.
Yes, almost there. But on the other hand, I can say, okay, resources. They probably have $200, for example. 20 years ago, now they probably have the same amount of money.
Tools.
Well, things
To
were
us. To us.
Things were a little bit simpler then too.
Say it again?
Simpler, I mean, the way you wrote code, the what you could execute, the environments that you could execute in, not as diverse, not as complicated.
No, actually,
So
to the opposite. The software system is much more complicated than before.
Oh, that's what I meant, that to do, maybe you could use other techniques as opposed to coverage. You know, like you talked about the code, when you code review.
Yes.
You could do that much more easily then than you could today.
Because it's a simple program. If it's a simple program, with the code inspection itself, you'll have good confidence. But if it goes bigger.
Complexity. So what you are saying, complexity is another factor.
That was
Okay.
a complex way.
Right.
Yeah, I was
Right.
thinking other thing too. Yeah,
But
not-
what John said, the tool support is
Yeah.
also the most key factor. Right. So now, statement coverage means what? Every line of code has to be covered, right? But what if you have 10 lines of code? Then you have to remember whether each of these 10 lines is executed. So, a simple way to explain this is that you are going to need to have a recorder. attached to each line of code. Do you really want to have 10 recorders? No. What if you have 5,000 lines of code? Then if the answer is no, what is a possible solution?
I think up to the decision point, we know that it runs sequentially. Right? So all the code from one decision point to the next one in one branch, that will get executed anyway.
It's almost there, right? They were
You can really-
executed together,
Yeah, right. It's a good
right?
together.
Just like this, C equals 0, I equals 0. That's what you said. You know, it's sequential. It's adjacent to each other. Unless there is an abnormal termination. Otherwise, execution falls through, right? And you also said that a decision, right? So why I less than 10 is separated from the previous two statements? Because it's a destination of a jump. It's a destination of a jump. During the second iteration, execution begins with this loop condition. Initialization will not be done again. So that's why it's a separation. And why the I less than 10 is separated from the loop body? Because the condition may be evaluated false in the beginning, and it will exit the loop without even going through the body. Okay, so that's basic block concept. So no, we do not need to have recorder attached to each line of code. We're going to figure out a way. We're going to do this control flow analysis, to group things together, because if one is executed, everyone else is also executed. So in this way, I can reduce the number of recorders which I have to insert. And decision. Should this be just one decision, true, false? Or should each member of it be evaluated to true and false? So that's something which you need to consider, right? It can be a very complicated compound decision. The entire loop condition, this whole thing, right? You can view as a single decision, or you can decompose it. How about this data flow? Let me first explain the definition and then show you the difference between the data flow and the techniques which we already discussed. Sometimes, when you want to cover a statement, statement coverage only says what? I need to come here and execute it. Agree? But suppose I have two paths. Before this statement, I have an if condition. Depending on the value of A, X will be defined differently. So far, so good? So with respect to this, I say I want to execute this statement. I can have my definition of X either from the truth branch or from the false branch. I have two different definitions. And from the statement coverage point of view, I don't care which definition I use, as long as one of them takes the execution to my destination, then statement is covered. So far, so good? But C use, P use, data flow says different. It says what? you need to make sure this definition comes here, and make sure this definition comes here. It's a pair. You have definition and use. Okay, when you have more than one definition, you want to make sure the first definition comes to the use. The second definition also comes to the use. And how about PUs? If you have a definition here, and later on you use the value of x in a predicate. So you have a definition x here, and you have a use in a predicate. Right? Then you have to say from this definition to the use, and then you go to the true branch, or you go to the false branch. Okay, so PUs means what? You have definition, you have a use in a predicate, and then tell me which branch do you go. So far so good? So that's what it says. Look at the blue curve. You have a definition here, you have a use in a predicate, and then whether it's evaluated to true or false. So you have definition, use, true, definition, use, false. That's PUs. So far so good? How about CUs? It's used in a computational statement, definition, use. So if you have two paths, first path, second path, for coverage, they only care whether this statement is executed. I mean for statement coverage. But for CUs, you have to make sure not just this path, but also a different path are also executed. So far so good? Now let me ask you a question. What is the difference between boundary value analysis, decision, condition coverage, predicate testing, and the PU's coverage, which we just discussed? Boundary value analysis, it tells you you need to use the value at the boundary, near the boundary, such as it's a good idea to make sure whether the program behaves correctly when you have A equals B. That's boundary value. Agree? Decision, true, false. Right? Predicate testing, you are going to have a set of variations, such as A equals B, A greater than B, A greater than equal to B, and so on. And you need to have a test case to separate the predicate you have in hand and its variations. So it can help you to catch a bug and give you a suggested fix. So far so good? But we also talked about for the predicate testing, it only works for certain type of predicates. Remember, has to be singular, and or a special type of non-singular. And decision, no limitation. Okay, now, can someone tell me the difference between decision coverage and the PUs? We just discussed the PUs. Looks very similar to decision, right? What's the difference between these two? Can someone tell me? What is the difference between decision and PUs?
PUs only tells that you are using it in the predicate.
Well, predicate is decision. This predicate can be very complex, can be simple condition, can be compound decision. It's the same. Decision coverage is also applied. Predicate is a generic term. Right? So all this forward can be applied to test predicate. So what is the major difference between PUs and decision? What is decision? True, false. Agreed? What is PUs? On top of that,
Assignment.
you have to tell me where the definition comes from. Agreed? You have to tell me where the definition comes from. So you say A equals 3x. PUs means what? Definition? Use, true branch. Definition, use, false branch. So far, so good? And we all know that for a computer program, it is very likely that you have more than one definition for a given variable, right? So I'm going to have A equals 5y minus 2. Agreed? So with respect to this definition, use true, false. With respect to this definition, use true and false. For decision coverage, it only cares whether the decision is evaluated to true or false. Does it care from where the definition comes? For decision coverage, they don't care whether A got its value through this statement or A received the value from this one. It doesn't care. It only requires you. This decision has to be evaluated to true or false. So you'll probably end up with what? Here, it's evaluated to true by using this definition. Agreed? And evaluated to false using this definition. You can do it, right? Now what is missing? You're missing definition false, definition true. So PUs requires you what? For each definition, use pair true false. So for this definition, use true false. This definition, use true false. And decision doesn't care which definition you use. Agree? So tell me, which one is stronger? Stronger means requires you to do more testing. Right? PUs, right? So actually, PUs is kind of what? A superset of decision. Agree? So, ask you another question. Suppose I have my first definition here, my second definition here, along the same path. I have the third definition. It happens, right? You can redefine the same parameter again and again in the program. Agree? Okay, now, for this case, how many PUs do we have?
2.
Why?
Because what all it matters is just the definition just above that.
Right. This one is gone. The definition will not reach this use. It's rewritten, redefined. So far, so good? But of course, if I have a different definition come through this way, then I need to pay more attention. We have another definition, use true, false. So in other words, definition to use in between has to be clear. No redefinition. You cannot redefine. If you redefine, you override the previous value. So the value is blocked, will never reach the use. So far, so good? So now we understand statement, which is also called basic block. Why I say also called? Because we don't want to attach a recorder to each statement. We want to group statements which are always executed together as a group. Okay, so statement block, we're talking about decision condition. Okay, we'll explain. This decision means the whole thing. Condition, decompose. We'll talk about CUs, PUs. And why do we want to do so? Because we want to catch the bug at the early stage. And this unit will talk about white box testing with respect to the source code, program-based. After this, we're going to talk about how to apply coverage testing to your design model. Why do we want to do so? A few reasons. First, much easier to fix a bug because the whole artifact, the whole system is simpler. Another way is what? Another reason is people will do the code generation based on the model. So certain code can be automatically generated. If that's the case, then the focus is not on code. The focus is on the model. So state of practice. Don't be surprised when you realize that the test cases you created for the first project only gives you 50 or 60% statement coverage. So don't be surprised. Even the well-known studies, they only have 72, 70. So it's going to be extremely difficult by just using functional testing to achieve high coverage. It's going to be extremely difficult. In class, we used the triangle example. Remember last time? That is a special case. When you do 100% requirements-based coverage, you also have a very high code coverage because the program is so simple. When you increase the complexity, implementation, even though there is a good traceability between the requirements and the source code. But the source code can be much more detailed. Okay, so the structure can be much more complicated. It's not just that you have 100% requirements-based coverage. You are going to execute every branch of the decision. It's not going to happen. So don't be surprised if you only see 50%, 60% of coverage of your program using the test cases you generated. So what do we want to do? We want to give you measurements. More importantly, we want to help you do the enhancement. Any commercial tool will tell you what has been covered, what is still missing. What has been covered, what is still missing. Any tool will tell you. The question is, do you need help in creating additional test cases so that the coverage can be increased in an effective way? You don't want to follow this path over this path. Yeah, people argue the more test cases, the better. But this has to be under one assumption: the test cases are effective, right? You don't want to use a lot of redundant test cases. So if the focus is to improve the coverage, you keep repeating test cases which go through the same chunk of code. It's not going to help you too much. You got 100 lines of code. You keep testing this 50 lines of code and leave the other 50 aside. It's not a good strategy, right? You want to make sure that every part is executed. So you want to improve the coverage in an effective way. Now, I only know 30% of the code is covered, 70 not covered. Among this 70, what should be covered first so that my coverage can be increased effectively? Just like, we got 9 students here. Suppose I need to visit every one of you once during the semester. I got 9 students. I have visited the first 2. I still have 7 students. Suppose you all live, on different streets. What is my best strategy? Ask everybody to the same room. What is the best strategy? So I need to think, if I go to visit him, then maybe just before him, I pass by Andrew's house. Then I kill 2 birds using 1 stone. Right? That's what I want to do. I mean, the most straightforward way or the most naive approach, which is not effective at all, is that I make a special trip to each of you. That's this one. That's not good. When I visit you, maybe on the same trip I can stop by, other students' places. Then I can improve the coverage effectively. Now the question is that which one should I visit first?
Which has more dependent nodes.
Almost there, dependency. Then how to get it? I have to do what? Control flow analysis. I have to analyze the control flow graph to see, if you depend on me, then, probably I can do both at the same time. So you have to do this kind of analysis. And in class, we're going to go through the details. But for your project, this has to be what? Become part of the tool which you use. Okay, it will do the analysis for you. It will show you which part of the code should be executed first. So many commercial tools, they only have what? Two colors, white or non-white. Non-white means what? Not covered yet, right? But what we say is that in addition to not just non-white, among the uncovered code, you need to prioritize. You need to compute. You need to compute the weight. That means what? How many additional coverage will you be able to accomplish? I want to visit you on the same trip if I can also stop by 2 additional places. So I actually visit 3 instead of 1, right? If I go to visit you and you are so far away from everyone else, then I don't have additional benefit except, by visit you. So that is something which we're going to discuss. How can I know which part should be red, which part should be yellow? And what does these numbers mean? That's something which we're going to discuss. And so the code in white is already covered. I don't want to touch it again. And the code in red is something which I want to do. And we can also have the decision coverage, right? So true and false branch, you're going to have different colors because they give you different additional benefit. And for this one, the false branch already covered, but true branch not covered yet. So that's something which we are going to discuss after the break. Okay, so measurements, easy. Already show it to you. The challenge is the enhancement. So we are going to explain how to compute the weight. Okay, how additional coverage can you achieve by going through certain uncovered code. You need to do some analysis so that you can improve the coverage in an effective way. Before the break, you mentioned this has something to do with the dependency. Think about this. These 2 statements, if I realize that no matter which path I go, every execution before it reaches this statement, it has to go through another statement, A and B. I cannot go to B without going through A. Then from coverage point of view, which one will you pay more attention, A or B? B, right? Because if I cover B, this one will be covered as well. This is before the execution goes to B. So A dominate B, but it's before the execution. So it's predominant. So far so good? Mm-hmm. But the execution does not terminate when it goes there, right? After B, it will go somewhere. Mm-hmm. If I can do another type of analysis, which shows that every time when the execution leaves B, it has to go through C before the program execution terminates. It doesn't matter which path you go. You can go this path or make a big detour back and forth, but you still have to go through C before the execution ends. Then, do I have to worry about C? I don't. Why not? because I know if execution comes to B, it will have to go through A, right? And once the execution leaves B, it has to go through C. So if I cover B,
You've got A and C.
I got A and C guaranteed. So I'm going to do this type of computation with respect to each node, each statement. Right? So B is here. I cannot go to B without going through A. So if I cover B, I have 2. If I also know that after the execution moves away from B, it has to go through C before the execution terminates, then coverage of B also guarantee the coverage of C. So I have 1, 2, 3. I'm going to give a value of 3 to you. Okay. This is the conservative approach because what we just said, guarantee. I cannot go to B without going through A. I cannot exit. The program will not terminate without going through C. So A, B, C bundled together.
So the weightage is given for each statement?
Yes.
For each
For each statement, when we talk about statement coverage, and then for each branch, when we talk about the decision coverage, and then for each CUs, when we talk about CUs coverage, depending on which coverage criteria you are talking about. Okay, this is what? This is the conservative approach. But we also know that the actual execution depends on the value at the runtime. So when the execution comes to B, the only thing which I can guarantee is what? It will go through C before the program execution terminates. But before it goes to C, will it visit other nodes, other statements? That's uncertain, depending on the value. Right? So that means B probably will go to E first, and then go through C. B will go to X and Y and Z, and then go to C. Right? So when I say I cover B, I will also cover A and C. I give a value of 3. And people will say, no, the actual value probably is higher than 3. It's higher than 3 because B probably go to X and then C. B go to alpha, beta, and then C. Or B go directly to C. But I don't know which path it will follow. So I choose the conservative approach. What I give is what? Guaranteed, the minimum. The minimum. Right? So that's what we are going to discuss. So a basic block. What is a basic block? We just discussed. They're adjacent to each other. Execution just falls through. But the one which we just discussed, A, B, and C, they don't have to be adjacent. Right? B can go to E and then go to C. B go to alpha, go to beta, then go to C. So A, B, and C now becomes a super block instead of a basic block. So basic block statements have to be adjacent to each other. Super block, you are going to have blocks separate. They don't have to be next to each other. But from the execution point of view, they are always executed together. Let's look at one example. Look at this chunk of code. And the right portion, the right part, is the control flow graph. Let's refer to this piece of code. Execution cannot go to 2 without going through 1. Right? Every time when execution goes to 2, it has to go through 1. So 1 is predominant 2. 1 predominates 2, right? Every time when execution goes to 2, it will not exit unless it goes through 14. So 14 post dominate 2. Therefore, we are going to say 1, 2, 14. They can be bundled together because one is executed unless it's a normal termination. The other two will also be executed. So 1, 2, and 14 together give you what? Yes. How about 3? Can we go to 3 without going through 2? No. So that's why 2 predominate 3. We have 1 predominate 2, 2 predominate 3. That's why we have here 1 predominate 2, 2 predominate 3. So far so good? And how come 3 and 4? 3 and 14? There is no predominant relationship between 3 and 14. Why not?
It doesn't have to go to 3.
3 is here. I can go to 3. 14 is actually dominant 3, but it's afterwards, not before. Go to 3, you don't have to go through 14. After the execution visits 3, before it terminates, you have to go through 14. So from predominant point of view, 3 and 14, they have no relationship. 3 and 14, you can go to 3 without going through 14, right? But once the execution goes to 3, you have to go through 14 before you can terminate. So that's why 14 post-dominate 3. 14 post-dominate 3. But 14 is not predominant 3. How about 3? Does 3 predominate 14? Let's check.
No, from 2 it can directly go to 14.
Yes. So can I go to 14 without going through 3? Yes.
Yes.
Therefore, 3 does not predominate 14. Is this clear? How about 4 and 5? Can I go to 4 without going through 5? After I visit 4, do I have to go through 5 before the program terminates? So 3, neither predominant nor post-dominant. So that's, let's take a look at 4 and 5. 4 does not predominate, does not post-dominate. 5, and vice versa. 4 and 5, there is no relationship. 4 and 5. No predominant, no post-dominant. So far so good? So what is predominant? I cannot reach, if A predominate B, I cannot go to B without going through A. Okay. C post-dominate B. I cannot terminate without going through C. Once I'm at B, I have to go through C before it can terminate. So therefore, if I coverage B, if I cover B, the coverage of B will guarantee the coverage of A and the coverage of C. Is this clear? So you just count how many statements, how many nodes predominate you, how many post-dominate you. You add them together. That is what? The minimum number of additional coverage in addition to yourself. And this value can be higher because you may have a detour, but there is no guarantee. So far so good? So let's, yes?
So let's say C is post-dominant to B.
Mhm.
Is it right to infer that B is predominant to C?
Not necessary. Not necessary. Look at this one. 14. Post-dominant 3. Once you go to 3, you
Right.
cannot exit, right?
Oh, I see.
You have to go through 14. 14 post-dominant 3. But 3 does not predominate
Yeah.
14.
I'm looking at from 2.
Right. So if you search the literature, you will find that most papers, they only talk about predominate.
Predominant, yeah.
Yeah, because that's easy to understand. I cannot go to B without going through A. Therefore, if I cover B, I will cover A as well. Right. But they forgot execution does not stop after it reaches B. It continues. Right? So you need to include what else will also be guaranteed after the execution reaches B. So you also need to consider the post-dominant. Okay. And then you add them together. That's how we decide the color. Right. So you have the predominant tree, and you have the post-dominant tree, and you are going to put them together. But then you notice what? I don't need so many extra ages. For 1, 2, and 14, if I comes to 1, there is a path from 1 to 2. There is a path from 1 to 14. Right? I reach any of this, the rest will also be reached. If I come to 2, there is a way go back to 1. There is another path which takes me to 14. Is this clear?
This is confusing to me. Yeah.
What we want to explain is, look at this one. I cannot go to 2 without going through 1.
Right.
So I cannot exit once I reach 2 without going through 14.
Right.
Right? So 1 predominant 2, 14 post-dominant 2. So 1, 2, and 14, they will be bundled together.
Right. Right.
Okay. What is the definition of a superblock? It says what? If any statement is executed, everyone else will also be executed. From the execution point of view, they are glued together.
Right.
One is executed, everyone else is guaranteed to be executed. What does this mean? One is executed, everyone else is guaranteed to be executed. That means if I go to you, I need to find a path to go to everyone else in the same superblock. Otherwise, how can I say one is executed, everyone else will also be executed?
Did you just mean the graph was confusing?
Yeah, I mean, I didn't get why it is going from 2 to 1.
That's
confusing.
here.
That was
Yeah, that's,
confusing
that,
to me.
I
Yeah.
just, the
It's-
concept was.
The concept is clear, right?
Yeah,
Okay.
concept is clear.
Now,
Yeah.
what we have, look at this one. What we do is that we merge these two trees.
We merge.
This is predominant, this is
Trying to show
post-dominant.
Clockwise and counterclockwise.
See, look at this one. I have 1 to 2, 2 to 14, right? 1 to 2, 2 to 14, okay? So I have 1 to 2, 2 to 14. This age and this age inherited from predominant tree. So far, so good? How about the other two?
Right.
14 to 2, 2 to 1. Because 1, 2, and 14, I'm going to put them together. And then I also inherit all the ages. You see what I'm trying to do? I just merge these two trees.
Yeah. a different color would have been better. I mean the arrows.
Predominant probably black and the post-dominant
Yeah, right.
red.
Right.
Then you know which one is from the predominant, which one is from the post-dominant. Okay, what we are doing is that look at this part. There's 3. You merge with this 3,
Yeah, got it.
right? So that's why you have 1 to 2, 2 to 14. You also have 2 to 1, 14 to 2,
Yeah.
right? So that's why you also have 2 to 1, 14 to 2. And then exactly that's what you point out. It's confusing. So let's just merge them together. Then, by definition, what does this mean? 1, 2, and 14 in a simple super block means what? There is a path from 1 to 2, a path from 1 to 14, a path from 2 to 1, 2 to 14, 14 to 1, 14 to 2. Right? That means if one is covered, everyone else will also be covered. But instead of showing you this without going through the details, it's maybe difficult for you to see, okay, you have a path from any given node to everyone else. So far, so good? Once again, you say, if I'm at 1, I have a path from 1 to 2. I have a path from 1 to 14. If I'm at 2, I have a path to 1. I have a path to 14. If I'm at 14, I have a path to 2 and then to 1. So you can, at any point, and there is a path from that point to everyone else.
You know, can you really though have a super block of 5 and 6 though?
5 and 6, let's double check. 5 and 6, okay, so 5 and 6, in order to put 5 and 6 in the same super block, I have to guarantee you, if I cover 5, 6 will be covered. If I cover 6, 5 will be covered. Okay, let's check. So that means if 1 is covered, everyone else should also be covered, right? So let's check 5. If I cover 5, I have no choice. I have to go through 6, right? So cover 5, I have to cover 6. Agree? Now, the other way, if I cover 6, do I have to cover 5? You ask yourself, is 5 a predominant for 6? Can I go to 6 without going through 5?
It is in this graph, but I guess in the, back to that other slide. Yeah, keep going. I was just looking at those 2 side by side.
Yeah, this one.
Because it looks like 8 can launch into 6
8. Okay, so
on the left.
so 8 and 5, they are not in the same super block. Each node, so here we kind of group together. 1 to 14 is the one super block. 5 and 6. Look at this. If I'm at 5, there is a path go to 6.
Oh,
If I'm at 6, I have a path go to 5.
you know what it is? Yeah, that
Now how about 8? Let's check. 8. Okay, so I'm at 5. 5. Do I have a path to 8? I don't. Do you see a path from 5 to 8?
No,
Okay.
but I see a block path from 8 to 6 in that graph. That's
8 to 6. Okay, now fine. Then how about 6? Do you have a path from 6 to 8? 5 and 6, they will be combined together. Because you are at 5, you can go to 6. You are at 6, you can go to 5. Well, one is covered, the other will be also. So 5 and 6, actually, this part, you can condense to just a single node. Doesn't matter whether it's 5 over 6. You are at 8, yes, you can come to 5, you can come to 6. 8 to 6, 8 to 6 to 5, okay.
I guess, yeah, that's probably, that's.
But you are at 5, do you have a path to 8? You are at 6, do you have a path to 8? You don't. That's why they are not in the same super block. Let's say this one more time. What we want to do, we want to say that if one is covered, the other will also be covered, and vice versa, in order for these two to be in the same superblock. Agree? Okay, there's A and B. You want to put them in the same superblock. If you cover A, you need to make sure B is covered. If you cover B, you need to make sure A is covered. So either one is covered, the other also has to be covered, so that they can put in the same superblock. If this does not hold, you cannot put them in the same superblock.
I think what it is, I know what it is, that I was just, I guess, misinterpreting when we got to the side-by-side on that, where you had the pre and post together, that I was misinterpreting that 8 to 6 relationship, just from that graph, because it looked like you could get 2 6 from 8.
That's
And that's what I thought, well, if you can just launch directly into 6 if you can get to 6 from 8, you don't have to go through 5. But that's not what that means, I guess. So,
Can we go to what you said is that I cannot go to 6 from 8.
post-dominant,
Right, that's post-dominant.
post-dominant.
Right,
And that's
it's not
what's
predominant.
Kind of confusing.
Post-dominant means what? Once I'm at 6, I have to go through 8,
Yes,
right?
yes.
But it's not that I have to go through 8 in order to reach 6. It's different.
Sure, absolutely. I was just misinterpreting that. I mean, because by the time we get down to that view of it, I mean, I can see here,
Right.
6 can go to 8. You know,
Yes.
I can see that direction, but on the next one, it shows 8 with the arrow back to 6,
Yeah, right.
which
I mean, in the post denominator,
in the
Post
post,
dominator.
that's what it
yeah,
does.
that's what it does.
Right.
From 8 to 6,
Because
you
you
will
know
have the
you're
arrow.
going from the bottom, essentially, you're really going bottom
Yeah.
up.
We're talking about pre and the post
Post, yeah.
together.
Yeah, yeah,
They shouldn't be together.
No, because, see, okay, let's just hold this question for a few more seconds.
I'll hold
and
it
then,
forever. I'm done.
and then we'll explain why we have to consider both. Okay,
So
so,
the computer will do this. You don't have to do it manually.
oh, that's true, right? So, now, okay, let's put that question aside for the time being. When you have predominant, post-dominant merged together, and then you remove those redundant edges,
I see. Okay.
you put them in the same node. So have you noticed what we just said? If I go to one of them, there is a path to everyone else in the same superblock. Agree? So if I'm at 1, there is a path to 2 and 14. I'm at 2, there is a path to 1 and 14. I'm at 14, there is a path to 1 and 2. So I just need to reach one of them, there is a path which takes me to everyone else. Okay, so this 1, 2, and 14 bundled together. And this component has a spatial terminology, has a spatial name in graph theory. Does anyone know what is the name for a node with this property? Superblock is what we just explained. So can anyone think of the name for this kind of node? That means if I reach 1, everyone else there is a path. Loop, not really. Root. It's called strongly connected component.
Oh, the thing in blue.
Right. So strongly connected means what? 1 is connected to 1 is connected to 14. 2 is connected to 1. 2 is connected to 14. You know, everyone is connected with everyone else. So far so good. So what is a superblock? You are looking for strongly connected component. So far, so good. So once we have this one, then do we need 2 edges? We don't. So we can remove one. And we are also going to remove this actual edge. So I have one path. I don't need to show 2 paths. So I'm going to simplify my graph to this one. Once I do this, I can start to compute the weight of each leaf. So let's count. Why do I have a value of 6 here? Because execution comes from the beginning, go through A has 3. Go to B has 1, 4. Go to C has another one, 5, and then 6. So if I cover number 9, this will be guaranteed to be covered. How did I get 8? 1, 2, 3, 4, 5, 6, 7, 8. How about this one? 9. 1, 2, 3, 4, 5, 6, 7, 8. How about the other way? 1, 2, 3, 4, 5, 6, 7, 8. Why did I put 9 there instead of 8? Look at this one. How did I get 8? 1, 2, 3, 4, 5, 6, 7, 8. How about this one? 1, 2, 3, 4, 5, 6.
You can reach it in 2 rounds, 2 different rounds.
2 different routes. Give me a more precise explanation.
Because you could go, well, you have that many in common, 1, 2, 3, 4, 5, 6, 7. It shares 8. I mean, yeah,
You have to
between
count
8
8 and 13.
It's actually
Why? Why do I know I need to count 8 and 13, but why?
Yeah, if you can
8
only
and
go,
13, yeah.
Why?
you can only go one path.
So that's her question. See, she said only one route, right? But then why do I include both 8 and 13? Why? This is directly related to the question she asked.
It is.
Because one is
Pre and post.
predominant, another one is post-dominant. Look at this. 8 and 10, 13 and 10. 8, 10, 13 and 10. Number 8. Number 10. Okay. I can go to 8 and exit without going through 10,
Yeah, right.
right? So that's what 8 and 10, they are not in the same super block.
Right.
But I cannot go to 10 without going through 8,
8, right.
right? So 8 is my predominant. Okay, that's why 8 should be included if 10 is covered. Agreed? How about 13? 10 is here. I can go to 13 without going through 10. Therefore, 13 and 10, they are not in the same super block. But once I go to 10, I cannot exit without going through 13. Therefore, 13 and 8, one is pre, one is post. They have to be both included. That's her question. Why do we need to consider pre and post? Why do we want to merge 2 trees? Because when you talk about the guaranteed coverage of a given node, once again, I cannot go to B without going through A. I need to include A, predominant. That's why 8 should be included when you count the coverage of 10. Once I go to B, the execution does not terminate without going through C. So C should be included. So once I come to 10, I cannot terminate without going through 13. Therefore, if I cover 10, 8 and 13 will also be covered. That's why you need to have what? Both. That's why I cover this. Look at both 8 and 13, they are dimmed. They're guaranteed to be covered. One is predominant, one is post-dominant. So far so good? And after the first execution, you need to quickly recompute. You need to recompute the weight. Because before the first execution, you have a value 6 for number 4. 1, 2, 3, 4, 5, 6. But once 10, 11 over 12, once they are covered, from the beginning along the path to number 4, you only have 1 remaining uncovered. Even though it's still same path, but some of them already covered. So covering them again does not improve your coverage. Therefore, the weight is reduced from 6 to 1. And here, 8 to 3. How come 8 to 3? Because 1, 2, 14, 3, and 8 already covered. Only 3 remaining uncovered. So in the beginning, your target will be what? This one. After the first execution, the target is this one. And then the remaining, they have the same priority. You just pick one. That's why you have, this is how the coverage will be improved.
Is this 9 over 14, 12 over 14, 13 over 14?
Right.
You do the deltas. 64, 86, and 93.
So if we use the super block concept, we don't need to have a recorder attached to every statement. We can reduce the amount of instrumentation. The amount of instrumentation can be reduced. Right? So it can be reduced to probably 1/3, as you can tell. About 30%. So if you have probably 1/3, 33. Is this good enough? Yes, instead of 100 recorders, now I only need 30%. Right? Otherwise, if I don't do the basic block, I don't do the super block analysis, I'm going to have a recorder attached to each statement. Now I do the simple analysis very fast. I reduce to just 1/3. The next question is this good enough?
Do we have any more money left?
So the tool which you are going to use only perform basic block and super block analysis. So this is with respect to the same control flow graph. It's what? With respect to the same module. Look at what we discussed here. I give you a piece of code. You generate control flow graph. Agree? And then you do all this dependency analysis. You got a basic block, you got a super block, so you can reduce the number of recorders to 1/3. So far so good. That's the tool which you are going to use. This tool is actually, developed, used to be called Bell Communications Research. Now it's called Telcordia Technologies. Okay, and Bell used to be the research institution for the baby bears. And long time ago, it's part of AT&T Bell Labs. They only do the intro. Now the question for you is this enough? Think about this. Here is one module. Execution come to this point. A equals function alpha beta, and then continues. Execution comes here. Yes, with respect to this module, just one statement is covered, right? But with respect to the system, it's more than one statement, right? You have another function here. The control will be transferred to a different function, different module, right? And continue. Agreed? And come back. Make it even more complicated. At this point, it goes to another function and then come back. So from the system point of view, how much additional coverage? It's more than one. You need to consider not just intro, INTRA, you also need to consider between modules, because at the end, what we are looking for, we're looking for the coverage of the entire system. And we're going to come back to this point, whether that's really what you want, coverage with respect to the entire system, or coverage with respect to a selected module. We'll come to this point later on. But from the overall picture, from the overall point of view, you did not include this part. If you only do the analysis within the same module. Agreed? So you also need to consider the inter. And that is much more complicated, much more complicated. So I was on the team. We developed this tool together. Okay, I'm going to give you a demo. And after I came to UTD, a few years later, they got money from US Army to do the second release and include inter-analysis. And they actually came here 3 semesters ago, and we did some experiments. Asked the students in class to use both intro and inter to see the difference. Okay, so by this time we're not going to do it. Nevertheless, we want to let you know, not just within the same module, but you can consider additional coverage from other modules as well. But the concept is still the same. Okay, you want to make sure if one is covered, the other is also covered, and vice versa. If you can do so, then they should be merged together. So from the basic block, that means what? Statements are adjacent to each other. This is the most straightforward way. Everybody can tell. You move on to super block. Now they are not necessarily adjacent to each other. Right? Look at this 1, 2, and 14. 1 is here, 2 is here, 14 is here. They're not adjacent to each other. However, from the execution point of view, they are always executed together. Okay, super block, this is, we only use one control flow graph for the analysis. And we all know that execution can go to different modules. So we need to consider inter. So we have this mega block. That gives you what? More precise analysis. So far, so good? Now, interesting question for you. We all know, okay, analysis based on super block is not as precise as mega block. Agree? Because it only considers the analysis dependency within the same module. Okay. In other words, when I say there is a guarantee of 50, for example, additional statement to be covered if execution goes here. If I say that, because I only consider intro, the same modules, so the actual improvement will be higher or lower or the same if we consider
It will be higher.
the inter. Higher, lower, or the same? Higher, right? Because when I say at least 50, but just doing the analysis with respect to one module, but it's very likely when execution goes here, there is a function call, something else will be covered as well and then come back. So when I say 50, it's still what? It's still safe. Right? Minimum 50. The actual improvement can be higher. Okay, so what do I lose? Because the analysis is not as precise as this one, if I also consider the interdependency between different modules. So what do I lose? So I probably think I should create an input value which takes the execution to this point so that my coverage can be improved by 50. But if I consider the global dependency, I probably should have a different red spot, which says 70, right? So I probably should create a test case which goes to that part because that gives me the global view. It guarantees 70. Without that information, even I just use the intro within the same module, it says 50, but at least 50. Maybe it can also reach higher, but at least 50. So I don't really lose too much. The worst case is what? Probably instead of 5 test cases, to achieve alpha percentage, I have to use 8 test cases to achieve the same coverage, right? So from one point of view, you may think, hey, instead of using 5, now you have to use 8. But on other point of view, every one of them still can improve the coverage in an effective way. We never say it is the best way. No, we never say that. We only say it is an effective way. And besides, variation is good. instead of, once again, spending time to figure out all this complicated analysis, I would rather use the time to execute the program with one more test case. You see what I mean? So yes, theoretically, this one does not give you the whole picture. It only does the analysis within a given module. Agree? If you have a function call, the actual coverage improvement will be higher. But now we don't consider that part. So our analysis is not as complete as we want. But it's simple, right? So if we include everything, probably I should cover this because it gives me 70 globally. And this one probably only gives me 60. So from the global point of view, I probably should cover this first instead of this one. Agree? But since I don't have that global analysis, this one says 50, and here probably 40. That's why I chose 50. However, all these are relative. When I say 50, minimum 50, probably can go higher. Right? So instead of spending time to do this complexity analysis to get 70 from the global point of view, I do the simple analysis, right? I got 50. So it can improve the coverage still in an effective way, even though it is not the best way. Agree? And I can save the time to run 1 over 2 more test cases. So every time I go for the so-called a better solution, I probably reach alpha percentage using 5 test cases. Now I don't do those complicated analysis. I can still probably reach the same coverage using 8 test cases. Yeah, from the test execution point of view, I have to run 3 more. Right? You may think that's not good. But from the testing point of view, I run 3 more. It's not a bad thing. Instead of spending time to figure out all this interdependency, this complicated analysis, I would rather spend time what? Run a few more test cases. So far, so good? And there is one more question which you have not thought about. You can do all kinds of analysis. Okay, I tell you. This is the point which I should execute first so that the coverage can be improved, right? What did I give to you? The destination. You need to come here so that coverage can be improved effectively. Is this enough? From tester point of view, I said, hey, you need to give me an execution which goes to here.
You have to figure out the inputs for that.
You need to figure out the inputs.
That's the tough part, right?
You spend so much time to tell me, come here. Okay. Which input values? We'll take the execution there. Right? So it's not that, yes, get the red spot is good. It's much better than existing technique, many other commercial tools. They only give you the measurements. They don't tell you how to do the enhancement. And this tool, so far, it do this, all this, for example, they give you different colors. You know you want to go for the red spot. But you still do not have the actual input values, which take the execution to the red spot. That's your second project. I give you the hints. What if after 10 minutes, after 20 minutes, you said, sorry, I just cannot figure out an input value which will take the execution to the red spot. What are you going to do? You're going to say, fine, I don't have the input value to hit the red spot, but I can have a different input value which takes me, for example, to the yellow spot, which is not too bad either, even though it's not, as good as I want. But it's not too bad either. And besides, when I say good, when I say bad, it's what? Guaranteed value. The actual improvement, maybe going through the yellow one is actually better than the one going through the red. It's just that the minimum, the lower bound, the red one is better than the green one, or better than the yellow one. But the actual execution, maybe you have 3 bonus points, right? And besides, if you spend so much time, still cannot figure out which input value will take the execution to the red spot, don't worry. Choose a different one, the next one. Even though the guaranteed value is 1/2 less than the preferred one. But you already got the input values. Why don't you use it? It still improves the coverage in an effective way. And besides, the actual improvement, maybe it's a surprise for you. So I want to emphasize, we never say that. Okay, use this approach will give you the best test cases that improve the coverage in the most effective way. No, we don't use most effective way. We say in a very effective way. It's a trade-off. You don't want to spend too much time just to figure out the input values and so on. Bottom line is still we want to do more executions. Okay, so if I have to do 3 executions to reach alpha percentage, and you say you can only do 2 to get alpha, but you have to spend 2 days to figure out the input values. I do 3, and I just use 1 hour to figure out the input values. Which one will you use? Even you say, okay, you have alpha plus 2, I only have alpha. It doesn't matter, I only use 1 hour, you use 2 days. Which one are you going to use? Is this clear? Okay. So we're going to, just explain the technique. Oh, one thing. During the break, one of you asked me an interesting question. Coverage. I have a system with 35 components, okay, 43,000 lines of code. Do I want to measure the coverage with respect to the entire system? Depends on you. Some probably will say, yes, I want to see the overall coverage for the entire system. And other will say, well, I got 3 components, A, B, and C, for example. A is initialization. I don't worry too much. C is the report generation routine. It can be important, but in my case, lots of data flow, data in and out, but the logic is pretty simple. So I don't care too much about A, I don't care too much about C, I pay more attention to B, right? So when I measure coverage, I probably will drop A and C. I only focus on B. So technique, we already discussed. When you talk about tools, the tool has to be flexible enough so that don't measure coverage with respect to A, with respect to C. You just slow it down the execution, too much overhead. You have to provide a way for users to do selective instrumentation. If I only care about this part, hey, just measure this part for me. Forget about everything else. Therefore, when you do the instrumentation, you have to be able to do it in a selective way. Selective instrumentation. And more importantly, when we report coverage, use the example which we just mentioned, we have a large set of test cases. A large number of test cases. So I have suppose 40,000 lines of code. Okay, so I have 15 components, just for example. And I have 5,000 test cases. I can do instrumentation with respect to the entire system. I can run over 5,000 test cases and give you a single number, the coverage. That is not so useful, right? And what if I'm only interested in components 1, 3, and 5. And I only want to know how these 3 components are executed when I use these 3 test cases. Right? Why? Because if this particular execution fails, then I want to know how the program is executed so it can help me do debugging. So I'm only interested in one particular execution with respect to some selected components. Can you give me the coverage? Can you tell me which part of the system is executed? So you have to be able to decompose the information, not just with respect to different parts of the system, but also with respect to selective executions. And that's the tool which we are going to demo. So that's okay? Okay, so this is called Software Understanding and the Diagnosis System. That means it's more than just testing. So testing and the debugging bundled together, that's the first 2. And then it also do the regression testing, do what? Program comprehension and performance profiling. So we're going to explain each of these during the rest of the semester. But today, let's focus on code coverage. Okay, so you can Google it. But to download the software, you need to have a password. Okay, but to just to see the first page, the home page, you can Google it. So we're going to give you a demo. Remember, in order to know which part of the program is executed, you need to have a mechanism to do the bookkeeping, right? To do the recording, which is instrumentation. So when I have a program with 10 lines of code, I have to know how many super blocks do I have and what is included in which super block. I have to know this so that later on I can do the report. So I have to do the instrumentation. And this is based on what?
Static.
Static structure. Once the code is fixed, how many super block is fixed? Which statement goes to which super block is also fixed. So this is static. That means you can do this at compiler time. When you compile, you parsing it, you recognize the structure, you do the instrumentation. So in the beginning, we have two source files. And I don't know whether you have used other commercial tools, for example, the one Purify, which detect the memory leak, right? So that means you're going to compile your program the same way as you do, but during this process, you are also going to link the tool.
Yeah, right.
So that the code, the executable, is instrumented executable. Okay, so yeah, so if you have the experience, you know exactly what I'm talking about. So we don't want to change, the way which you compile. We just want to add additional link so that it will do the instrumentation. It will generate an instrumented executable. So instead of a CC, you have a tag CC. That means when I compile the source code, I also want to do the instrumentation. So after that, after the compilation, you will see you have two static files. That is what? How many attributes and the location of each attribute. So far so good? So you still got your executable. But in addition to executable, you also have static files. Now I'm going to show you the source code before the AD execution. You are going to open the instrumented source code. So go to the right directory, main and word count. No test case, 0%. Here is my red spot. So you can see, different values. That means if you cover code in this color, guarantee you this much additional coverage. So far so good. Nothing is covered. So what I'm going to do, I jump to the red spot because it has the highest value. I need to figure out an input which takes the execution to this spot. Before that, remember what we said? Software quality, you have dynamic, you have static attributes. Static attributes means user's menu, one of them. So this is thumbnail image. You click on it, you're going to see the enlarged picture. So far so good? That is the second homework. You're going to go through it. I'm going to have an execution go through this part and see how the program can be covered. So I come here to do the execution. I hit return. So you need to do the output verification by yourself. Okay, this tool is just what? Coverage measurements. It doesn't do test generation. You generate the test. You execute it. You have to verify whether the output is correct. If yes, you're going to see what has been covered. If not, the information which you have collected so far should be hooked with what? A debugging tool to help you find out where the problem is. And that is the third project which we talked about. So far, so good? Okay, we have done the first execution, and you verify the output, and you're happy. It's correct. Okay, let's see how the program has been covered. We want to make sure this one is covered. And let's see whether something else will also be covered. Look at this. It's going to change to white. And many other things are also covered.
So that trace file is generated when you executed the program, is it?
Yes, that's runtime.
The runtime. So that's because of your instrumentation, you got outputted particular file.
Say it again.
How did that trace file get generated? Is it because of the instrumentation that?
Because of the instrumentation. Right. What is instrumentation? You can just think, okay, I have many recorders at different locations. Each time when execution comes here, the count will be incremented by 1.
Yeah, but it is also routing it to an output file, right? So it's also opening an output file.
No, output, say this additional information which I collect is just for the coverage purpose. It's saved in a different file.
Right, yeah, that's
It's
what
a
I
different file. It's separate from the output due to the program execution. So because I did this analysis, so with just one execution, I can reach almost 70%. So let's look at one more time. This is my red spot. And I come here. So I just let you watch one more time. So you do this test generation is still your job. Verification, your job as well. But then we import the collected information. See, this is a trace file. And once we include that information, a lot of code has been covered and changed to white. And with just one test case, we have about 70% coverage. And then we can go to the next one. So you move on, go to the next hotspot. Okay, and then you read the source code, you will say, oh, this one is easy, I need to give an illegal option.
Can it tell you that, I mean, I would think it would be able to tell you, if it identified that spot at red, it should be able to tell you that 68.9 right then and there.
Just 1 minute. So because we have additional execution, so let's click on the update to import the information which you just collected, so the coverage is improved.
I see, okay. So
Yes.
the same output trace file, it updates it for each one.
Right, and you do not have to update the trace file after each execution. Okay, so every time when you have one execution, you have additional data collected
Into the same file.
into the same trace file. It keeps appending. Okay, so that's why when the trace file has additional information, the update button is in red. So you can choose to click on it or do not click. That means you can update the display. You can recompute. Already erased. Recompute the weight. So what is the trade-off between an update after each execution and an update after a few executions? The difference is not much. Okay, if I do the update after each execution, so the weight will be recomputed. I got a new hotspot, right? If I don't do the update after each execution, so based on one execution, I have a few points which I want to cover. Right? So I generate a test case, cover this one, and this one. Maybe when I do the first execution, some of the statement which is going to be covered by the second one has already been covered. Right? So the coverage increment, the improvement may not be as big as you think, but still it's an effective way. In this way, you reduce the overhead for the recomputation. But in general, it's very fast. But still, when the program is large, you need a few seconds, a few milliseconds to do the recomputation. Yes, your question?
So my question was, so you get to this point and you see your hot spot or the weighted, right, values. So can I tell from that red, and even at this point, knowing that I've already got up to, maybe I'm now at 74% coverage or whatever.
You can do that by just click on test case. So you said at this point, okay, you want to know the current coverage.
I want it, well, and you've demonstrated, we can see that now.
Yes.
So how much is white,
Right.
really? So now what I'm asking is, so if I can execute that hot spot.
This one.
What's that gonna do for me? What kind of bang for the buck on that particular one?
Before the execution? No, you cannot do it.
But why not?
Because it's not just the control flow analysis. I can execute this statement. This one is easy because it's a printf statement. It's a printf statement. But suppose this is like this: y equals a plus b. I can execute that statement, but the actual average, the actual coverage depends on the value of a and b. I can only tell you the minimum. If you want to see what is the coverage going to be after the execution of this red spot, I can tell you at least 9 additional statements will be covered. Exactly how many? It depends on the runtime value. Okay? So that's how we improve the coverage step by step. And then after 2, we have this coverage. Okay, now we are going to show that you don't have to do the update after each execution. So it says 50, 80%, then go to summary. Okay, here. So you can present the coverage information in different ways. Now we are trying to cover this part. So we are going to figure out a test input execution, which will take execution to the red spot. Okay, so but I don't want to update. I just run another execution. Okay, I check the output, and I do another execution. You can do the batch execution. Okay. So if you ask me, how do I know I should use this and that? Because I see the which part has not been covered, and based on my knowledge of the program being tested, so I figure out those, and then I update at the end. Everything is covered. So far so good. Okay, now, then you are going to see, okay, I got 100% with respect to statement. How about I switch to decision? Do I have 100%? Right. So this one says block statement, block statement. Okay. So you have 100%. With respect to the statement coverage, you are using the tool attack, and now we move to the decision coverage. You notice that they are only 78%. So you are going to tell me, okay, which part? You means the tool will tell you. Okay, the fourth branch already covered, another true branch. So you come out to figure out an execution which will touch that uncovered true branch. And then you do the output verification. You come here, you click on it, done. And then you go to the other red spot. Okay, summary, it's improved, but you can tell the improvement is not as big as the beginning. That is expected, right? The last one, when you have a switch statement, it tells you which case has been covered, which has not. Okay, so you come here and you do one execution. And you can do additional executions to cover the code which has not been covered yet. So let's do a few more to see whether we can have 100% decision coverage. So we're going to import the data, the trace information at the end. You click on this, it's covered, everything else is covered. You will reach 100%. So this is the second homework which you are going to do. You are going to try it in class, not just to achieve 100% statement basic block coverage, but also 100% decision condition coverage and 100% CU's PU's coverage. That's what you are going to do in class. Once you know how to measure the coverage, then the first part of your second project, you're going to repeat the same procedure. But this time is what? The test cases which you created for the first project. And you are going to see how much coverage
Oh, I see, okay. That makes sense.
you can accomplish by using the functional testing test suite which you created.
That's why you gave the source code for us.
Right. And then the second part of the second project is what we just did, improve. It shows you which part has not been covered. It gives you the hints that you need to come out with appropriate input values which improve the coverage. And we are going to discuss also, of course, probably next time, how to use the hints to generate the actual input values, which take the execution to that point. So now we tell you the measurements, right? We also give you the hints for enhancement. And we still have one more step to go. Use the hints to actually guide the test generation. So far, so good? So before the break, we just gave the demo of the attack coverage tool. But we mentioned when you do the testing, you always want to think ahead. You know, you have spent so much time and so much resources to collect the coverage information. Can the same information be used for other purposes, right? The same information be used for debugging. Some information be used to help you select which test cases should be re-executed during the regression testing. How to use the coverage information to help you understand how each functionality is implemented in a system. So that's traceability requirements versus source code. How can we use the coverage testing information to help you create this traceability? You know, the performance analysis. People say that I probably don't need help because I have other tools which can measure the CPU time. Okay, so you have a system with 50 components. You can say, oh, this particular execution takes 2 seconds, that one takes 3 seconds. I also know which component consumes the most computation power. Yes, you can do that. But can you identify which line of code in your system takes most of the CPU time? You can do this with respect to function, with respect to file, module. You have commercial tools. But what we can present to you is we're going to tell you which line of code is most frequently executed, or which basic block is most frequently executed. Because each basic block contains at most 3 to 5 to 6 lines of code on average. So we're going to assume what? The execution time for each basic block is more or less the same. You know, you only have 3, 4, 5 instructions. If this a basic block is executed 10,000 times, another basic block only 5 times, then obviously you know which basic block should be the target for you to improve the performance.
Yeah, so this is assuming that you haven't linked with any libraries, with any of the OS calls, nothing like that, right? It's just pure, your code, it's a pure CSS statements, that's what we're talking about.
It's execution frequency, how many times it's executed.
Right, I mean, so for example, if you have made a call to printf, okay, or you made a call to some function, some math function or something, you assign something. So that it can take any time, you know, that you cannot.
Yes, I agree with you. But it tells you, for example, how many times this particular function has been executed.
Oh,
But
not the
it-
time, not CPU time, but how many times it got executed.
Right, how many times it got executed. So it's a different perspective. Right, so if you see, you know, some part of the system is executed many, many times more than other part, then, and you're not happy with your performance. So that can be good candidates that you can explore, you know, whether that's the best you can do. Or, you know, if you can improve, for example, a particular function has been invoked 5,000 times and it's highlighted. So you're going to ask yourself, you know, can I improve of that particular function code? Right? It gives you additional hints about where to start the improvement. Okay, so all this is based on what? Coverage information. Because once we have a recorder there, you know, every time when execution comes here, the count is increment by one, and then by one. Okay, now we have an interesting question for you. Execution comes here and then go there, right? And come back. So now its count is 2. Right? Or execution goes here, go there, and then come back. The count is also 2. Okay. What kind of information should we collect? One is simple, just 0 and 1. 0 means not covered. 1 means covered. Okay, that's it. 0 and 1. Another one says no, 0 and non-zero. Okay, in the beginning it's 0, not covered. And then come here, 1, going there, come back, becomes 2, right? Come here, going there, come back, becomes 2. So both situation gives a count of 2. Execution frequency. Now the question is, should I remember the actual sequence? Come here, there, and here. That's one sequence. Come here to here and here. That's another sequence. What is this? This is the path. It's more than just 2 times. Right? So after statement coverage, basic block, decision, CUs, PUs, already PUs, CUs, we're talking about definition use. It's already a pair. It's just part of the path. Right? But beyond that, we have another coverage criteria, which is called path. Path can be very complicated. Okay, can we afford to do this? Technically, you want me to record the sequence, the exact execution sequence. I can do it. I can do it. Now the question is that even for a small program, even for a limited number of executions, think about this. One execution may be back, forth, go to right, go to left, and then come back and so on. It can be what? A very long sequence. Very, very long sequence. How are you going to save this information? The trace file becomes too huge. So from the coverage point of view, people say, hey, just record. Yeah, that's easy. In practice, when you talk about tools, you need to think about what? Trace information which you collected at runtime. It becomes more and more how to, manage. How to manage this data. So you need to ask yourself, what is your objective? I can record entire execution sequence after another sequence, after another sequence. Or I just record 0, non-zero. Okay, that obviously reduce the amount of data which I have to save. Okay, that's the first question you need to ask yourself when you talk about coverage testing. What should be collected at runtime and what should be collected at compiler time? Compiler time is what? How many different criteria you want to use? Just statements, or decision, or condition, or CUs, PUs. Okay. Now let's assume we just want to record up to the execution frequency. That means we use 0, non-zero. Okay? Now, think about the following. You have a program with 6,000 lines of code. Let's say just 6,000. It's really small. $6,000 lines of code, 300 test cases. What I want you to record is how many times each basic block is executed. Very straightforward. How are you going to design the mechanism to help you save this information? At runtime, in the beginning, 0%, nothing is covered. The first execution, something is covered. The second execution, something is covered, right? In order to report what has been covered, the information collected during the first execution has to be saved in the trace file. How are you going to save this information? Second question. Suppose 150 components, 6,000 lines of code. I want to do coverage of component 3, component 5 with respect to test 12. How to quickly extract the information. from your trace file. Everything is saved there. Everything is saved there. Okay, each attribute, in our case, each attribute is a statement or a basic block. If it has a count of 0, means not covered. It's a count non-zero, 1 over 2 over 3 means covered. Okay, so now you understand the question. We already discussed the technique. Since we don't want to do it in hand, we have to implement a tool to do this for us. And we all know that we need to collect lots of data during runtime. And in each execution gives you additional data. You keep appending more and more data into your trace file. This file management is a very big challenge. That's to be efficient. Nobody is going to sit here wait for 5 minutes before you report the coverage. Any suggestion? What kind of data structure we have to use for this trace file? We're going to have a big trace file. Yeah, people argue you can have many small trace files. Yeah, we actually did that. It's very complicated. But to make the discussion simple, okay, before we touch that, let's say we only have a trace file which collects all this runtime data. What kind of data structure will you recommend? Remember, after each execution, more data, more data, more data. You have 6,000 lines of code. Suppose each statement, that you have 6,000 attributes. And 300 test cases. You need to know how the program is executed with respect to the first execution, how it's executed with respect to the second execution, and so on, right? What kind of data structure will you recommend?
Vector?
Almost there. Almost there. Say it again. Yeah, we're going to, related to vector. So
The data for each test run, save it.
yeah, data for each. Of course, you have to save it. If you don't, when I say I want to have the coverage with respect to a particular execution, how can you retrieve it? So the easiest way, let's start from the easiest way. The easiest way is what? Oh, it's simple. Let's have a big two-dimensional array, right? So 6,000. 1, 2, 3, 4, 5, up to 6,000.
But it will be blocks, right?
Okay, block.
Yeah.
Let's say 6,000 blocks. Over 6,000 true false branch. Doesn't matter. 6,000 attributes. Okay. T1, T2, T3, T300. That's the most straightforward way. If it's covered, it's 1. If it's not covered, it's 0. Covered 1, 0, 0, 0, 1, 1, 1, 1. Right? Advantage of this is what? I want to have the 12th execution. Take the row out. You got it? I want to have combination of the 3rd execution and the 5th execution. Take this 2 row out. You got it? I want to have the 3rd component, the 5th component with respect to the 5th execution. Take 2 columns out, 1 row. You have the information right away. So far, so good? Looks like a good structure. Retrieve is very efficient. But the problem is, okay, 6,300. You think you can handle it? I'm going to increase this to 50,000. I'm going to increase this to 6,000. Yeah, you do have this system. 6,000, 5,000 test cases, 500,000 lines of code. Are you going to have such a big two-dimensional array? Probably not.
No, For each one, you can save it as one separate file.
You're going to have how many files?
300 files.
Or 6,000, it changes it to 6,000.
You're not going to survive. You're not going to survive. In fact, for this tool, each execution in the beginning is saved as a separate file in the temp directory. And then that's the keyword. Condensed. You have to do this. But on the other hand, you still want to keep the good property. I can take the first row out, the first column out. I can slice the data any way I want, horizontally, vertically, right? Okay, now, I don't want to use this big two-dimensional array, but I still want to keep this efficiency. Okay, coverage with respect to the first test case, take it out. Coverage only for the third column, take it out. So he already hit the keywords. How to, in the beginning, you said, okay, the first execution, information is saved in the temp directory. Once the execution is done, I have to what? Append information to the end. But I don't want to give the whole row, right? I want to condense. How to condense?
Just all the non-zeros.
Almost there. Say it again.
I said all the non-zeros.
All the non-zeros. Do you need 10 consecutive zeros? Just one zero.
Talk about Huffman coding.
This is called. This is there are certain algorithms which
Runtime, run-length coding.
something like that. There is more than one way. We are not telling you which mechanism you are going to use, but we give you the concept. So you need to condense it. Why you can do so? Because the coverage matrix, this is coverage matrix. This is coverage. The coverage matrix is a there are so many different ways. Why it is a sparse matrix? Think about this. One execution, you got 60,000 500,000 lines of code. A lot of part is not even touched. It's zero. Why? Why do you want to use so much space to save a bunch of zeros? So you need to use very efficient algorithm to condense it. And then you can easily take the row out, take the column out, decompose, report the coverage right away. Okay, that is the mechanism which we used for this tool. So far, so good? So I have a few more points which I want to discuss with you. So this one was developed when I was with the Telcody. I was one of the team members. And in fact, during the break, we talked about the user's manual was done by me. So enjoy reading the manual. And how about Java code? How about bytecode? Right? So because we are talking about white box. White box based on structure. Concept is the same. But when you talk about code coverage for C program, code coverage for Java program, for C++, for C#, they're all different. Concept is the same. dominant: super block analysis, control flow analysis. There's visualization, prioritization. But because the underlying syntax is different, so the parsing will be different. Instrumentation will be different. So you can Google it. You go to the, I think we discussed this before. You can go to go to Avaya's website. You can search for ExVantage. That is the tool which initially implemented by us at UTD. And then we deployed to Avaya. And then they did additional enhancement. Okay, this one is for what? For Java code, Java bytecode. You don't even need source code. Now, I have additional questions for you guys. Everybody now understand what code coverage testing is. We talked about this runtime data collection. We also say you have to determine what kind of data should be collected at the runtime, at the compiler time. Should I just count 0, non-zero? Or should I include execution frequency? Or should I actually record the exact execution sequence? You are dealing with different amount of data. Okay, let's say you only do up to execution frequency. Suppose we only do up to this point. That is the current version of Keras. But this time, I'm not talking about a PC application. I'm talking about an application on an embedded chip, embedded system. We're talking about embedded system. Okay, that's the project which we did for Texas Instruments. What's the difference between PC platform and an embedded system?
Resources.
Memory. They don't have enough memory. Are you going to have a huge trace file on a target system? No way. Then what should you do? You still need to collect the information, but your target system does not have enough space for you. Okay, some people will say, why don't you, collect information and then communicate and transfer to a PC host?
Yeah.
Ideally, you can do that.
Yeah.
Yeah, they don't have this communication channel. So
Basically, when you run this code coverage, this is your running it during development phase. It's not on a production system, right?
Depends. For example, for the target system, sometimes they have this device driver. Device driver is very small size program. So it's part of the system. They want to measure the coverage. And they have to do this because we got this project for a very simple reason. We're talking about OMAP or MAP. I don't know if you know it. Okay, so the buyer simply told TI, tell me, how did you test your software on the OMAP? Yeah, you can use emulate. That's something which we're going to discuss later on for the next class. We can do simulation. What is simulation? Simulation is similar to functional testing for program. You treat the entire program as an entity. Emulation, simulation, the same. Black box. But this time, the buyer says, tell me the coverage. So you have to use white box. How to measure the coverage for an application on a target machine when you don't have enough memory for you to save all the data collected during runtime? Any suggestion? I mean, The principle, the technique is still the same. It's just that what? You need to figure out how to save the data. Another question, which we did with NASA. This time, it's the real-time applications. What's the major difference between real-time and
Yeah.
average PC application?
Timing.
Timing.
These, tools, you cannot have the instrumentation. You cannot go with counters, you can't add like that. Then the
Maybe,
timing-
maybe non-deterministic. Okay, same input may give you different output depending on when the signal, when the other inputs
Right.
come. How do you deal with this type of application? You do the instrumentation, super block, yes, it reduced to 30%. But still too much overhead. So you have to further reduce the instrumentation. But if you sacrifice too much, then you don't collect enough information. What should we do? We actually used, a similar approach to solve both cases. So let's talk about the embedded system, the target machine. So I cannot collect the runtime data on a target machine because I don't have enough space to save the information. But what I can do is what? I can record the key point of the execution sequence. I don't do the data collection, but I remember the execution sequence. How do I remember execution sequence? For coverage, for data collection, remember I said I have recorder associated with certain key statements, because one super block only need one. Right? Every time for the PC application, I go there, I do the data collection right away. Right? But this time, I don't do data collection. I just remember I come to this point, I go to next point, I go to next point. I don't record the entire execution sequence. I only memorize which recorder is executed, which recorder is executed. So that's what can significantly reduce the amount of data which I have to collect. And then I come to my host, PC host. I don't have the hardware support. I don't have the input. Do I care? I don't. Why not? I already know the execution sequence. Come to this point, I'm waiting for the interrupt. I don't have the hardware, but I know after this where the execution should go. Right? So I do two iterations, record and replay. The record is just recording some key sequence. Replay, I can do all kinds of instrumentation. I can slow down the execution because I know exactly what should be executed next. That's the simple description of what we did. Okay. Of course, details is much more complicated. But you use these two iterations. You don't do the data collection
Like
directly.
a core dumps, like.
Kind
In
of.
the sense that, you save
But
it
we
to
don't
the-
dump that much information.
Right. I mean, you save it to a memory, and then after the test.
I know the key component, how it will be executed. And then on PC host,
Then you can do the analysis.
I can do all kinds of data collection I want. I can slow down the execution. I don't even need input. Right? It's just like what one of you asked me. I have 10 components, right? If I just want to do testing, I guess you asked me, with respect to this component. I don't have the rest of the system. That's fine. You must have heard test harness. That's the same concept. I rub. Do I really need the input, whether it's directly come from the rest of the system or what just provided by me? It doesn't matter. Right? I know it needs this, and I know what should go, where it should go after it receives the signal. That's good enough. I don't really need the hardware. So on my PC host, I don't have the hardware support, but I can still what? Replay what was actually executed on the target machine. And that is where, that is when I collect the data. Okay, so coverage testing can be very simple idea. But when you actually apply it in practice, a lot of details, a lot of details. Not just, the information which you want to collect, but also which platform. Lot of additional constraints. Okay, so this can be a very good topic for the term paper. For example, one of you, I think either this class or another class mentioned, they want to write a term paper, apply white box testing technique to database applications. That's a very good one. That's a very good one. You can say, okay, apply technique XYZ to applications from domain alpha. That is a very good one, especially if it is related to what you are doing